This particular lecture covers the topic memory interfacing and IO interfacing with 8085 microprocessor. So first of all, what do we mean by the interfacing? It says interfacing is a concept that refers to a point of interaction between the components and is applicable at the level of both hardware and software. This basically allows a component to function independently while using interface communication with other components via input-output system and an associated protocols. So whenever we are going to use any system, basically comprises like microprocessor, it requires input-output device as well as memory element. Before we feed any program or data into the system, it is required to interface earlier so that all the data and instructions can be stored easily and automatically during the time of programming the system. So what we basically require to interface any memory device or IO device with the microprocessor, three main component or main element that we required are the address lines, data lines, and the control lines. These are the very primary important primary component required for the interfacing a microprocessor with the input-output device or memory elements. In case of 8085, we know that it has 16 address lines which is divided into two sections or two parts known as higher order address lines and lower order address line. Namely A8 to A15 which is called higher order addresses and AD0 to AD7 which are multiplexed address and data lines. In addition, with the address data lines, it is required few control signals, namely ALE stands for address latch enable control signal, IO M bar line, RD bar line, WR bar line, and ready signal. So address line, what its purpose? Address line's purpose, it is used to address the memory or IO devices. When processor want to communicate any device, maybe in IO or memory, and it is known that in a memory there are so many addresses, so many locations, and each location of the memory is identified by its addresses. Similarly, there are number of IO device can be connected with the system, so each of the device having some particular address. So address lines function is to identify a particular memory location or the IO device before communicating any data or instruction with the memory element. So as it is said that address lines divided into two parts which is called higher order address and lower order address, A8 to A15 and AD0 to AD7. And this AD0 to AD7 also acts as a data lines for communicating the data or instructions to or from the memory. As 8085 mainly a 8-bit processor, so its instruction size is also 8-bit. So 8-bit data or instruction microprocessor communicates with the memory through the 8-bit data lines. So here is the summary. Higher order address line bus is a unidirectional bus. Why it is unidirection? One question may come. Higher order lines unidirectional because it only carries the address from the microprocessor to the memory, whereas we will found that AD0 to AD7 multiplex address lines are bidirectional because it not only send the address to the memory or IO device, but also it carries data either from the microprocessor or to the microprocessor. That's why AD0 to AD7 lines are bidirectional, whereas A8 to A15 higher order address lines are unidirectional. So A8 to A15 carries most significant 8-bit of a 16-bit address of the memory or IO device, and address remains on the line as long as operation is not completed. Throughout the cycle of fetching the data or accessing the memory element, the higher order 8-bit will remain present on the A8 to A15 lines. In case of lower order address data bus, this bus is bidirectional and works on the time division multiplexing basis between address and data. During the first clock cycle, for communicating the data with the memory element, it requires mostly three states during the first clock cycle or clock period. It carries the address, whereas during the next two states, that is called T2 and T3 states, it carries the address from the microprocessor or to the microprocessor. .8085 identifies a memory location with 16 address lines, AD0 to AD7 and A8 to A15. 8085 performs data transfer using its data lines AD0 to AD7. These lower order lines are multiplexed as earlier described, that for first clock period it carries the address, and for the second and third it carries the data. Demultiplexing refers to separate the address and data signal for read and write operation. So as the common lines are serving two purposes, that's why it requires demultiplexing, and demultiplexing is done in time division basis. How it is done? So why it is required? Now during the locating the memory element, all the 16 lines, address lines has to be present on the A8 to 15 and AD0 to AD7, whereas during the transmission of data, that same line to be act as a data lines. That's why AD0 to AD7 require demultiplexing, and demultiplexing is done with the help of the control signal ALE, which is called address latch enable. How it functions? Actually, during the T1 cycle, when microprocessor starts its operation for fetching any data or instruction, ALE signal goes high, and once ALE signal is high, the 74373 latch is enabled. 74373 latch is enabled. So whatever signal is present on the line AD0 to AD7 that is available at the output of the latch, and its lines now it is naming as A0 to A7. So once the signal of AD0 to AD7 present at the time of T1 and ALE is on, that is latch into the 74373. So now all the 16-bit address available at the output A0 to A7 and higher order addresses which are already available at A8 to A15. So that's how the address lines are demultiplexed from the data lines at the time of T1 cycle, and during the T2 and T3 cycle the data required to communicate are placed onto the D0 to D7 line, maybe from the microprocessor to the memory device or from the memory device to the microprocessor. Now during the T2 and T3 cycle, this is going to be acting as a data lines. So here is the summary of the previous picture, that ALE signal enabling that 74373, and the input of the latch is available at the output of the latch acting as an address, and A8 to A15 address are available for T1 to till the end of the completion of the transfer. And once the memory element particular section is enabled, then the data of that particular section is communicating through the data lines. So AD0 to AD7 now acting as a data lines for the rest of the cycles. Next comes very important control signals, read and write. We know that microprocessor is capable to read from the memory or write into the memory. So what action is performed or what microprocessor want to perform, that is indicated by its control signal known as read RD bar and WR write. These are read signal and write signals are active low signal. That means when microprocessor want to read any input output device or memory device, this RD signal goes low. Similarly, write signal, that is WR, when processor want to write any data to the memory device or IO device, WR signal goes low. By default, both the signals are high. That's why this RD signal and WR signal known as active low signal. And next important signal is the IO M bar signal. As microprocessor access both the memory device and IO device, so whether processor is now accessing the memory or IO device, that is indicated by the signal IO M bar. IO M bar signifies what? Here when IO is active high, whether M bar is active low. That is, when microprocessor want to access the input output device, this particular signal will be high or logic level 1, whereas during the access of memory element or memory device, the control signal will remain low. That's how processor separates the input output device and memory devices. Now combining these three signals, how memory read, memory write and IO read, IO write is generated is shown here. First, if we consider memory read signal, first we consider the memory read signal. This signal is enabled when processor want to access the read the memory device. That's why, as it is the memory related operation, so IO M bar signal is low here. IO M bar signal is low here, as well as it is a read operation, that's why RD signal, read signal is low. These two signal, with the help of these two signal, our NAND gate is generating the active low pulse for the memory element. So among all the signal, it is found that here at the input side both are 0, IOM bar and RD bar is 0. So these two signals are connected with the NAND gate through to NOT gate. That's why ultimate input of the NAND gate are 1 1, and when NAND gate input becomes 1 1, it is low. So during the time IOM bar equals to 0 and RD bar equals to 0, it produces active low signal, and it is using to activate the read operation of the memory. Similarly, during the memory write operation, like before, here also the IOM bar signal is low. Now WR signal becomes low to indicate that it is a memory write operation, and combining these two, like previous case, here active low memory signal is generated. Now when processor want to access any input output device, as it is described earlier, that IOM bar signal will now become 1. IOM signal now become 1, and for the read and write operation, like before, RD bar signal goes low for read and WR signal goes 0 or low for write operation. For the time being, IO read operation, IOM bar is 1 and RD signal is 0. So combining these two, here double NOT gate is present. Before the NAND gate, two NOT gates are present. So ultimately at the input of the NAND gate, 1 is present, and IOM bar signal is already 1. So this combination produces the active low signal at the IO read operation. And finally, for IO write operation, here WR signal is 0 and IOM signal remains 1. And combining these two, IO write signal is produced. So once we found that what are the main component or element is important for accessing the memory device or IO device, now it's time to talk about the memory. What type of memory are there, and with microprocessor 8085, which memory are connected. It is well known fact that we are having two types of memory, that is the primary memory and secondary memory. Primary memory, ROM and RAM comes under this category. For accessing the data fast, these two devices basically used. Hence, the speed of this type of memory should be very high to access the instruction and data very quickly. And in case of secondary memory, to store the bulk amount of data or information, generally secondary devices are used, and hard disks, CD, DVD, this kind of memory device come under this category. And obviously it is non-volatile memory, whereas RAM and ROM volatile memory, that is once power is off, data from the RAM will disappear. In case of interfacing memory elements with the microprocessor 8085, we will be talking about the interfacing of RAM and ROM. So before we observe the final connection or circuit diagram, we must know what are the basic component of the memory. It will then it will become easier to understand why we require different signal for accessing the memory element. So inside of the memory we found very two important component. One is the D flip-flop and other is the tri-state buffer. These are the two common element we found inside the memory. D flip-flop, very well known as the data flip-flop, used to store 1 bit data. Its output equals to input. If we provide the input as 1 and enable the control signal EN, then the data will be latched into the device and it will also available at the output. So, and what is the function of a tri-state buffer? Now, to control the flow of data either at the input terminal or output terminal, we use tri-state buffer. Tri-state buffer having the characteristics that there are 3 terminal is present. This is the input terminal, this is the output terminal, whereas C is the control terminal. C controls the flow of data from the input to output. So in case of this diagram, this control is active high type. That means whenever control pin is 1, then only input will available at the output, whereas if the control is 0, then no input will transfer to the output. Here it is shown, if the control signal is 0, then no matter what is the input at the output, it will not be available. That means output will be at high impedance state, no signal will be there. But whenever the control equals to 1, then output depends on the input. So as there are 3 states we observe at the output of the tri-state device, that is either 0, logic 0, either logic 1 or high impedance state. That's why this device is called tri-state device. Moreover, active low control signal may also be present, like it is shown in the next diagram. Here the control pin is active low type. This tri-state buffer control pin is active low type. That means here if we provide the control signal as 0, then only the signal present at the input will available at the output. Otherwise, if the control signal is 1, then no information can pass through the tri-state buffer from the input terminal to the output terminal. Here active low type tri-state buffer is used. Basically we have seen that read signal or write signal of the microprocessor basically are active low type. So combining these two devices, that is the D flip-flop and tri-state buffer, ultimately produces one particular memory device, one memory element is capable to store only 1 bit information, there are 2 buffer we can observe here. This is known as input buffer and this is known as output buffer. Input buffer is controlled by the WR pin, whereas output buffer is controlled by the RD pin. So if anyone wants to store any data into the D flip-flop, 1 bit data into the D flip-flop, first of all we need to enable the enable pin of the device or D flip-flop. Then if we apply the input over here at the input terminal and enable the right control signal, the data will be latched into the system. The data will be latched into the system, and the latched information, if we want to read or access, then as like before, enable signal must be on, as well as read signal is to be activated now to get the output which is stored inside the D flip-flop at the output. So for this overall picture gives us a presentation or image how 1 bit information can be stored into the system. Now previous diagram, here it is shown that previous diagram multiple number of D flip-flop connected together. Here 4 D flip-flop is shown which are connected together to form one 4-bit register. 4 D flip-flops are connected to combine and make a 4-bit register. Here it is observed that the enable pin of all the D flip-flop are connected together to make a single enable pin. Similarly, the read control of all the tri-state buffer are connected together and makes one common read terminal. Similarly, input buffer control terminal are connected together and make a single control terminal as WR. Whereas the input lines of each of the D flip-flop through the tri-state buffer are individually present, I0 in the form of I0, I1, I2 and I3, to provide the 4-bit input to the memory, whereas the output of the tri-state buffer are also individual to get the separate information that is present individually in the memory element at the output. So once we want to access this 4-bit register, then first of all enable terminal is to be on or activate. Then depending on the read in operation or write operation, we need to enable the write pin or read pin. Then only data to be stored we can store into the system or memory, and data to be accessed present in the memory element are available at the output O0, O1, O2 and O3. So once we get a 4-bit register, then this 4-bit register, multiple number of 4-bit register can be combined to form a complete memory. So in this picture, in the next picture, only 4 registers are combined together, known as register 0, register 1, register 2 and register 3. And as we can observe that there are 4 input lines, I0, I1, I2 and I3 present. That means each registers are 4-bit in size. That means the diagram shown before. And similarly, the output buffer, all the output buffer enable pin, that is the RD pin, are common here, and input buffer enable pin common here. But to access the different memory register element like register 0, 1, 2 or 3, we require now address. Which particular location we want to access, that now will depend on the address line. Properly we need to address the section which we want to access. That's why address line is required. So as there are only in this particular diagram 4 register element is present, that's why 2 address line will be sufficient. 2 address through the decoder can produce 4 combinations as 00, 01, 10 and 11. So 2 address lines will be sufficient to access the 4 register element, and this output of the decoder are connected to the enable pin of each register shown in previous diagram and enable the particular section, and depending on the address we will be able to access the memory and store or read the data. So with this we conclude the first section, first phase of memory interfacing. In next phase we will study about the how memory of different size connect with the microprocessor. Thanks.